We invest millions into training the neural network weights of a language model, yet the procedural code wrapping that model, the harness, is routinely left unoptimized. Researchers typically focus strictly on these frozen weights to improve a model's underlying reasoning capabilities. The harness is the stateful logic that dictates exactly what that model sees. It controls what information is retrieved, what is stored in memory, and how context is structured. Empirically, the harness matters as much as the model itself. Swapping the harness around a fixed language model can create up to a 6-fold variance in the exact same benchmark performance. Despite this impact, harness engineering is still treated as an artisanal process, driven by human heuristics. The standard workflow involves engineers manually reading through failure logs and hand-coding fragile logic rules to manage context better for the next run. Treating these stateful code architectures as a simple text optimization problem falls short. Tweaking a prompt template is insufficient to resolve the complexity of an agentic system. Standard automated text optimizers attempt to solve this through iterative refinement. Methods like OPRO and OpenEvolve generate new prompts based on historical performance feedback. These systems rely on a compression trap. To fit execution history into a context window, they reduce complex task runs down to a single scalar score, or a short LLM-generated summary. Harness code operates over long horizons. A misconfiguration at step 1 can silently poison context, causing failures 20 steps later. When that timeline collapses into a single score, the causal link is lost. The optimizer cannot trace the downstream error to its origin. The information deficit here is strict. Traditional optimization methods hit a hard ceiling, processing roughly 30,000 tokens of feedback context per iteration. That budget is microscopic compared to the diagnostic footprint required to actually evaluate and debug complex Python execution traces. Automating harness engineering requires a system that abandons compressed summaries. It must expose the raw diagnostic footprint of every failure so the optimizer can see exactly what broke. MetaHarness is an outer-loop system designed specifically to bypass the compression trap and search directly over executable code. The architecture consists of a frozen, inner-loop language model executing the target task, monitored by an autonomous coding agent acting as the proposer. This proposer functions as a coding agent with full terminal access, navigating files and rewriting scripts directly. This setup breaks the traditional context limits. While legacy text optimizers operate with 0.03 million tokens of context, MetaHarness operates in an environment containing 10 million tokens. That represents a 3-order-of-magnitude increase in the diagnostic information available per iteration. Those 10 million tokens comprise the unedited source code, the exact prompts generated, the tool calls made, the raw model outputs, and scores from prior attempts. This token expansion allows the coding agent to natively process raw execution logs, diagnosing failures from the actual data rather than lossy interpretations. The coding agent does not ingest all 10 million tokens in a single prompt. That would overwhelm any context window. Instead, MetaHarness structures its memory as a persistently growing file system. Every evaluated harness generates a dedicated directory for its raw data. The outer loop proposer traverses this data using standard terminal commands like grep and cat to search across directories and pull up specific logs. By running these queries, the agent actively filters the 10 million token history. It retrieves only the exact log files relevant to the current failure mode it is trying to solve. Based on the filtered data, the agent then writes and proposes entirely new Python code structures for the next harness iteration. While older methods merely filled in blank spaces within rigid templates, this process generates novel logic autonomously. The agent decides which past architectures to inspect and pull inspiration from, without any hard-coded rules dictating its selection. Treating optimization memory as a queryable file system allows the agent to navigate a vast, stateful code space, making targeted improvements based on historical evidence. Because the coding agent reads broadly across prior logs, its diagnostic methodology shifts to identifying systemic, repeated failure modes rather than isolated errors. For example, the agent can observe an incorrect system output and trace the execution path backwards to find a faulty memory update that occurred several steps prior. Viewing the raw execution trace allows the agent to isolate the exact variable or logic rule responsible for the downstream failure. Once the flaw is identified, the agent deletes the faulty logic blocks and writes new, optimized structural modules directly into the system codebase. This expansive action space contrasts with hard-coded mutation structures, which restrict optimization to superficial parameter tweaks. The freedom to execute deep structural rewrites is only possible when the full causal chain of execution remains visible to the agent. An ablation study using an online text classification benchmark reveals how much these raw execution traces impact performance. This chart shows the performance disparity across feedback modes. Restricting to scalar evaluation scores results in 34.6 median accuracy. LLM-generated summaries yield virtually identical results at 34.9. When we introduce the full meta-harness interface, median accuracy leaps to 50.0. The implication is clear. Summaries actively compress away the precise diagnostic details required to fix complex code. Raw, uncompressed traces are mandatory for optimizing complex logic in any automated engineering system. In online text classification, we can compare meta-harness directly against agentic context engineering, the current human-designed state-of-the-art. The architecture discovered autonomously by meta-harness outperforms the human-designed baseline by 7.7 points. We must determine if this performance increase relies on injecting more tokens into the prompt context to buy accuracy. This plot illustrates the Pareto frontier, showing the trade-off between task accuracy and context token cost. Meta-harness establishes a position high on accuracy and strictly low on cost, utilizing 4 times fewer context tokens than the human baseline. Agentic algorithmic search redefines the efficiency frontier of context management beyond human heuristics. A high score on a target task introduces the risk of overfitting. We have to verify if the search loop discovered universally good logic or merely memorized prompt tags. To test this, the discovered harness was deployed on highly complex, previously unseen IMO-level mathematical problems. The results held. The single retrieval policy discovered by the agent improved mathematical accuracy by an average of 4.7 points across 5 entirely different held-out models. This cross-model success proves the agent discovers universally reusable algorithmic structures for reasoning. The traditional approach to scaling AI capabilities involves training larger neural network weights, often spending immense compute for minor benchmark gains. The next major gains in AI performance will derive from structural code rewrites as agents navigate and learn from raw diagnostic memory.